Hi, this is Helal. In this video on Mathematical Economics series, we will solve another numerical on the applications of Hessian method in checking the second order conditions of a constraint optimization problem. The question is, maximize utility, that is u is equal to 2xy subject to the budget constraint 3x plus 4y is equal to 80. We are given a utility function, and with that we are given a budget constraint. Here 3x plus 4y is equal to 80. This means 3 is the price of x times x, which is the quantity, plus 4, which is price of good y, times y, which is the quantity of y. That should be equal to 80. So this is our constant, and we have to optimize the given utility function. So this is the case of a constraint optimization problem. Find critical points. Test second order condition using bordered Hessian. We have to find the critical points, or we say the optimal points, and also to check the second order condition using bordered Hessian. First of all, we have to find the critical points. Now, how to find the critical points? First of all, we have to form a Lagrange's function. That is, we form the Lagrange's function. Here I write this utility function, that is u is equal to 2xy, and we are given the constant 3x plus 4y is equal to 80. This is called the objective function, and this is our constant function. First of all, to form the Lagrange's function, we set this budget constant equal to 0, this constant equal to 0, and multiply it by the lambda. That is, so I will write here, if this is 3x plus 4y is equal to 80, first we set it equal to 0, so this will become 80 minus 3x minus 4y is equal to 0. After that, we multiply it by the lambda. That is, multiplying it by lambda will become 80 minus 3x minus 4y. So this is our resulting constant. Now, to form the Lagrange's function, we take this objective function and add it with the resulting constant function. So our Lagrange's function, actually I have made earlier videos on the constant optimization. You can check there the rules. So here I am not getting into the details. So our Lagrange's function is equal to, which is equal to the objective function plus the resulting constant function. So this will become, our objective function is this, so I will write 2xy plus this resulting constant function, that is lambda times 80 minus 3x minus 4y. So this is our Lagrange's function. Now to check, to test for the first order condition, that is, first we have to check the first order condition. For that, we partially differentiate this Lagrange's function with respect to x, y, and lambda, and set them equal to 0 simultaneously to get the values of x, y, and lambda, which may be the critical points there. So first we partially differentiate this Lagrange's function with respect to x. So I will write here L subscript x means partially differentiating this this Lagrange's function with respect to x. So this will become 2y. Now here this will become lambda times minus 3x, so this is minus 3 lambda, and set it equal to 0. Similarly, we take the partial derivative with respect to y, so this will become 2x minus 4 lambda is equal to 0, and similarly partially differentiating with respect to lambda, so this will become here 80 minus 3x minus 4y is equal to 0, or I can write this as minus 3x minus 4y is equal to minus 80. So it is very easy how we partially differentiate. If you have any doubts here, you can check my earlier videos where I have explained the partial differentiation. So after that, to get the optimal values of x, y, and lambda, we have to solve these three equations, this one, and this one. We have to solve them simultaneously. Now we have a method which we have already discussed in earlier videos. We can use the Greemers rule in finding the values of x, y, and lambda, that is solving the system of linear equations. So we will use the Greemers rule to get the value of x, y, and lambda. So here comes the Greemers rule. So I will write Greemers rule. First of all, what we do, we write them in matrix form. So the matrix form is A x is equal to B. Now I am repeating. I actually covered this Greemers rule in earlier videos. You can check out what does this mean. So I recap here. This is the coefficient matrix. This is the vector of constant terms. Sorry, this is the solution vector, and this B signifies the vector of constant terms. So I will form the coefficient matrix. That is the coefficients of x, y's, and lambdas. Here the coefficient of x is 0. So I will write here 0. The coefficient of y is 2. Here the coefficient of lambda is -3. Similarly here the coefficient of x is 2. The coefficient of lambda is y is 0, and lambda is -4. In this we have the coefficient of x is -3, the coefficient of y is -4, and the coefficient of lambda, since no lambda is here, so the coefficient will be here 0. After that, x is the solution vector. That is, I will write x, y, and lambda, which is equal to the vector of constant terms. Now our constant terms is 0, 0, and 80. 0, 0, and 80. So first, we to solve for Greemers rule, we express the given system of equations, linear equations, in matrix form, which I have done here. After that, we take the the determinant of the coefficient matrix. This is our coefficient matrix. Coefficient matrix, I will write here. This is the solution vector. This is the vector of constant terms, and so on. This is the vector of constant terms. So first we take the determinant of this coefficient matrix, that is, which is denoted by this. Now the coefficient, the determinant will be, so solving, now we write this 0 and delete the row and the column in which it appears and multiply the resulting determinant. So 0 into 0 is 0. Now this is -16. Now we have -2 and delete the row and the column. We are with 2 zeros are 0, -3 4s are 12. Now we have -3 here, deleting row and the column in which it appears, and take determinant of remaining elements. That is 2 into -4, that is -8, and -3 zeros are 0. Now this is equal to, now here 0 times anything is 0. So here -2 into -12, that is +24. So I will write here 24. Similarly here -3 into -8, that's +24. So this results out to be 48. Means our determinant is 48. So we have calculated the determinant of the coefficient matrix. Now to get the optimal value of x, or to solve for x, we form a new matrix, which is formed by, now to solve for x, we form new matrix, which is formed by replacing the first column of the coefficient matrix with the vector of constant terms and taking the determinant of the resulting matrix. So to solve for x, what will we do? We form a new matrix. That is, we form a new matrix. Let us say that is A1. So I will write here A1. To solve for x, we form a new matrix that is formed by replacing the first column of the coefficient matrix with the vector of constant terms. So this is here. So I will write 0, 0. So actually it is here -80. So I will write 0, 0, -80, and these two columns will remain same. So I will write 2, 0, -4, 2, 0, -4, and -3, -4, 0, -3, -4, 0. So this is our new matrix. After that, we take the determinant of this matrix. Now the determinant will be, so I will write here, the determinant of A1 is equal to, simple, we take this 0, and delete row and the column in which it appears and take determinant of remaining elements. That is 0 into 0 is 0, minus 16. Now we have minus 2. After that, minus 2. Deleting row and the column in which it appears, this row and this column, we are with 0 into 0 is 0. And 80, we have here 80 into 4, that is 360. So we write minus 360, and we have minus 3. Deleting this row and the column, we are with 0 into minus 4, that is 0, minus 0 into 80, that is also 0, which comes out to be, now 0 into anything is 0. Now minus 2 into minus 360, that is 2 zeros are 0, 2 6s are 12, 2 3s are 6 and 7. Now minus into minus is plus. So our determinant is 720. So this is the new matrix which is formed by replacing first column of the coefficient matrix with the vector of constant terms if we were to solve for the first element of the solution vector. Now to get the value of x, so to get the value of x, I will write here, to get the value of using Greemers rule, x is equal to, the value of x is equal to, that is the determinant of the new matrix, that is A1 divided by the determinant of the coefficient matrix, that is A. Now our new matrix, the determinant is 720, so I will write here 720 divided by our A is 48. Now when solving this, this comes out to be 15 actually. So the optimal value of x is 15. Similarly, to solve for y, we replace the second element of the coefficient matrix with the vector of constant terms and form a new matrix and take the determinant of that new matrix and use this formula. So our new matrix will be A2. Now A2 is equal to, that is, we have to replace to solve for y. So I will write here first, to solve for y, we form new matrix, that is formed by replacing second column, that is 0, 2, minus 3 will remain same, 0, 2, minus 3 will remain same. In place of 2, 0, minus 4, we have 0, 0, minus 80. So I write 0, 0, minus 80. And this is minus 3, minus 4 and 0. I will write minus 3, minus 4 and 0. So this is the new matrix which is formed by replacing the second column with vector of constant terms to solve for y, that is for the second element. Now taking the determinant of this A2, which comes out to be, now 0 into, now, and this is 0 into 0 is 0, minus 320. Now we have 0, minus 0, I will write here minus 0. Now here deleting row and the column, we are with 2 zeros are 0, minus 3 for the 12, and minus 3, deleting row and the column and taking determinant of remaining elements, that is 2 into minus 80, that is 2 into minus 80, that is 160. So I will write minus 160, minus 3 zeros are 0. Now 0 times anything is 0, 0 times anything is 0. Now here minus 3 into minus 160, that comes out to be 3 zeros are 0, 3 6s are 18, 3 1s are 3, and this is 4. That comes out to be 480. Implies our A2 is, so I checked this out to make sure that I didn't make any mistake. So we have here, this is 160, this is 3. Now this comes out to be 3 zeros are 0, 3 6s are 18, 3 1s are 3, that is 480. So our new matrix is 480. Now to get the value of y, that is using Greemers rule, our y will be equal to the resulting new matrix divided by the original matrix. This is 480 divided by our original was 48. So this comes out to be 48 ones are 48. So 48 zeros are. So this comes out to be 10. So I'm not sure whether I have done the calculations correctly. So you can check that the steps are same. Therefore, the optimal value of y will be 10. Similarly, to find the value of optimal value of lambda, we replace the third column of the quotient matrix with the vector of constant terms. So I will write here to solve for lambda, we replace the this with the vector of constant terms. That is our a3 is equal to, so 0 to minus 3 is same, 0 to minus 3 is same, this will also remain same, 2 0 minus 4, 2 0 minus 4, and minus 3 minus 4 and 0. In place of these elements we write 0 0 minus 80. So this is 0 0 minus 80. After that we take the determinant of this. So taking determinant, that is a3 is equal to, now 0, deleting row and the column, that is 0 into 80, that is 0, minus 4 into 0, that is also 0. Then we have minus 2, deleting row and the column, we are the 2 into 80, that is minus 160, minus 160, and 3 into 0, that is 0. Similarly, plus 0. We are with deleting this row and the column, that is 2 for the 8, minus 8 and minus 0. Now 0 times anything is 0, 0 times anything is 0. Now here minus 2 into minus 160, that is 2 zeros are 0, 2 6s are 12, 2 1s are 2, that is 320. So this comes out to be 320. So this is our the determinant is 320. Now the value of lambda using Greemers rule, also using Greemers rule, lambda will be equal to the new matrix divided by the coefficient matrix. The determinant of that is 320 divided by 48. So I repeat, I am not sure whether I have done the calculation correctly, but the steps are same. I repeat this. Now here it comes out to be that is 6 8s are 48. Here this is 6 5s are 30. 6 5s are 30. So let it be 320 divided by 48. 320 divided by 48. You can solve this. Because of the lack of space, I am not able to solve this entirely. Now I should rub something here. So our x is 15, this is 10, and this is 320 divided by 48. So I will rub this. Our x is 15, our y is 10, and our lambda is something like 320 divided by 48. So I should rub this now. So these are the critical points or the optimal points. So this was only the first order condition. Now we have to test the second order condition. So this was first order condition was there. First order condition was, we take first order condition was Lx should be equal to 0, Ly should be also 0, and L lambda should be equal to 0. This was the first order condition. That is that we take the derivatives of this Lagrange function with respect to x, y and lambda and solving them simultaneously to get the values of x, y and lambda. So these were the first order conditions which gives us the value of x15, y10 and lambda is something this fraction. Now to test the second order condition we use the bordered Hessian method. That is second order condition, or I will write SO. We use the bordered Hessian method. That is, we form a matrix that is this H cap or H bar. We form a matrix of the second order partial derivatives of this Lagrange function. That is, I write here Lxx, Lxy, Lyx and Lyy. So this is simple. This is a plain Hessian. So we form a matrix of second order partial derivatives of the Lagrange function and border this with the partial derivatives of the constant function. That is c of cx, cy, here also cx, cy, and we write 0 on the principal diagonal. So this is how we form the bordered Hessian matrix. Now the cx, cy, lxx, lxy, these are the derivatives which we have to find. Now moving on, our H2 is equal to H. That is, our H2 is also this whole matrix, 3 by 3 matrix, which is equal to, so I will write here first, we have 0 here. Now we take the constant function. Our constant function was somewhere, that is 3x minus 4y is equal to 80. So c is equal to 3x minus 4y minus 80. So this is our constant function. This is 0. Now the differentiating this with respect to x, so we get here our c of x is 3, cy is 4. So 3 and 4 we get here. That is differentiating this constant function with respect to x. Here this will be 3. Similarly, with respect to y, it will be 4. So here we have 3, 4. Also here we have 3 and 4. After that, we take the Lxx, means differentiating partially this very function. This function with respect to x. Here no x is involved, so here it is 0. After we have Lxy, that is Lx means with respect to y. Now with respect to y, this differentiation will be, that is 2y, the derivative of y is here 1, so here it is 2. Similarly, Lyx, this is our Ly. Now differentiating this again with respect to x, so here it is differentiating this with respect to x, we get here 2. So I will write here 2, and we have Lyy, that means differentiating this with respect to y. Since no y is involved, so here it is 0. So this is our bordered Hessian matrix. Now our second bordered principal minor is given by, we take the determinant of this, which comes out to be, that is, we take the determinant of this matrix now. So this is here 0 into, now here it is 0 into 0, deleting row and the column, we are with 0 minus 4, now minus 3, this row and this column, we delete this row and this column, we are with 3 zeros are 0, minus 4 twos are 8. Similarly, we are with this minus 4, deleting this column and this row, we have 3 twos are 6. This is plus minus plus here. This is 6, 3 twos are 6, minus minus 4 zeros are 0. So we are with this 3 8s are 24. So we write here, this is minus 3 into minus 8, that is 24. Now here this is minus 4 into 6. So I am here confused whether if it is here minus 4, this is plus, this is minus, this is plus, sorry, this is here plus. So here 6 4s are, it is also 24. Now which comes out to be 48. Here our second borrowed principal minor, which is H2 bar, which is called the second ordered principal minor. It comes out to be 48, which is greater than 0, which is here. When the second borrowed principal minor is greater than 0, we say this H is negative definite. We say H is negative definite. When it is negative definite, that means this L is maximized, implies L is maximized. So it was actually a long video, so I repeat here. To check the second order condition, we form a new matrix which is called the borrowed Hessian matrix, which is formed by taking the partial derivatives, that is the second partial derivatives of this Lagrange function, and we border these derivatives with the first derivatives of the constant. So this is our constant. We take the first derivatives with respect to x and y, cx cy. Okay. After that, we form this matrix, that is H2, which is called the second borrowed principal minor. So I will write this is second borrowed principal minor. Now we form this second borrowed principal minor when given the values of these partial derivatives, and if the value of this second borrowed principal minor is greater than 0, if it is greater than 0, we say that this matrix, which is also H, so I will write here these two are same, this H and this H2, second principal minor and this Hessian, these are same here. Now when this comes out to be greater than 0, we say that this H is negative definite. When H is negative definite, we say that this L is maximized. Okay. I hope I make myself clear. Actually, this is the crux of the earlier videos which I have explained, in which I have explained the whole this stuff using the Greemers Rule, or how we maximize or minimize, or how we use the matrices and determinants in solving the linear equations. So it was actually a farrago of more than one concept. I hope you enjoyed this video. If you really like this video, please subscribe and share. Thank you. Eyvallah.